Okay, dear students, let us start from where we left. Now, last time we talked about fundamental forms. Now, we have a surface whose equation is R is equal to R at UV, and U and V are two independent parameters, real numbers. And then we've got two quadratic forms in du and dv. The first one is e du square plus twice f du dv plus g dv square, and the second one is l du square plus twice m du dv plus n dv square. Now e, f, g are related to the surface by their numbers which are evaluated at a point on the surface. E is ru dot ru, f is equal to ru dot rv, and g is equal to rb dot rv. So they are numbers, and similarly we denoted another quantity, the magnitude of Ru cross Rv, which we know, which we showed is equal to square root of Eg minus f square. So these are called first order fundamental magnitudes. Then we also have our unit normal to the tangent, which is basically Ru cross Rv divided by its modulus. So we gave them the interpretation of the first fundamental form was that it is basically equal to ds square, where ds is a small arc length on our surface. While a surface, and you're taking a small element of the arc, that length square is equal to the first fundamental form evaluated at that point. Similarly, second fundamental form gave us the idea of how curved the surface is at a point, and once we evaluate these second order partial derivatives and dot them with the unit normal, we get second order fundamental magnitudes. So we have got second order fundamental magnitudes, or whatever we call them, coefficients or numbers. So they are evaluated at a point on the surface. So the interpretation was that it gives us half of the length. If I've got a surface and I've got a tangent plane at a, I don't know, मैंने इसको draw ठीक से नहीं किया, चलो फिर से करते हैं, try. Okay, the second order fundamental magnitudes was basically the half of the projection. So let me try to draw it again. So I have a surface, think of it as a surface. Okay, I am also trying. Then I have tangent plane at some point of the surface, and then I take a neighboring point Q. So it's a P, and I've got a tangent line at P to the surface, and Q is a neighboring point. It actually measures the second fundamental form, this perpendicular from the neighboring point Q to the tangent plane at P. Now we know that it would be 0 if the surface is flat, and basically PQ is half of the second fundamental form, this QR distance. And if it is bigger, the surfaces would be more curved there. And if it is now inversely, it would be inversely related to the curvature which we have not yet defined of a surface at that point. So let us move ahead. So let us take a simple surface and evaluate. There would be many more examples. You just have to evaluate these numbers, and then you basically have just to evaluate the partial derivatives of a surface. Now usually the simplest form of surface is what we call the Monge's form. And you know that many examples that we did could be easily reduced to a Monge's form. So Monge's form is the surface of this form if you can write z as explicitly as a function of xy. Then its vector equation is very easy to write because we can treat x and y as our parameters, and our surface would be simply x comma y comma f of xy. So this would be the vector equation of a surface if it is given explicitly. I have got z. If I take this my z-axis, and this is my x-axis, this is my y-axis, and explicitly given it as a function of xy. Okay, similarly then Ru would be nothing but No, first partial derivative, it would be derivative with respect to x. So that would be just nothing but 1, 0 del f by del x. And but when we write z is equal to f of x y, then we usually denote del z by del x or del f by del x is usually denoted by, now it's a convention, we denote it by p. So similarly, del f by del y, we denote it by q. It's the usual practice. Similarly, del 2f by del x square is denoted by r, and del 2f by del x del y is denoted by s, and similarly del 2f by del y square, second partial with respect to y, is denoted by t. We generally use these symbols, they are in vogue from when you do partial differential equations in x and y, then you know that you use these symbols. So I can similarly then write it as, in terms of new symbols, as 1, 0, p. And needless to say, r sub v then should be equal to 0, 1, q when you partially differentiate with respect to second parameter. No, you have to think of now, our parameters are, in place of u you have x, in place of v you have y. So when you partially differentiate with respect to u, it is the same thing as differentiating it with respect to x. So similarly, you can evaluate r sub uu. So you are differentiating it again with respect to x. So that should be, of course, 1 differentiated with respect to those, this should be 0. Then this should be del square f by del x square. But we know that del square f by del x square is denoted by r. Similarly, r sub uv should be, of course, again 0, 0. And you are differentiating this again with, now with respect to y. So when you have mixed partial derivatives, you denote it by s. And r sub vv, again using this notation, should be equal to 0, 0 t. So once we have these numbers, you can evaluate the first order fundamental magnitudes. You just have to use basically the dot product and cross product. And if I just have space there, okay, so these are the numbers now. Now what is E? First order fundamental magnitudes? Easy. So E is nothing but, my first order fundamental magnitudes E is equal to r sub u dotted with r sub u. So you have to dot this with itself, this vector, और 0, 0, इसको अगर खुद के साथ डॉट प्रोडक्ट ले तो क्या मिलेगा? This would be 1 plus p square. And similarly, you have f. You have to take dot product of this vector and this vector. It should be just, now it is basically ru dot rv, which is equal to simply pq. And if you take g, you have to take its dot product with itself, so it will be 1 plus q square. Now this is damn easy. And similarly, if you take h square, which is nothing but eg minus f square, you already have eg, then you have minus f square, so it will be 1 plus p square into 1 plus q square minus p का whole square. And if you simplify it, that is just 1 plus p square plus q square in terms of these symbols, p, q, r, s, t. Similarly, you can evaluate n. Now what is n? N is nothing but ru cross rv divided by h. H square you already have. You take cross product of u and v, what would be that? So cross product of u and v would be, you can easily check, but there is nothing. Okay. you can check it is, you can evaluate it, it's very easy. It is minus q p minus q 1. You just have to take the cross product of RU and RV. So first would be 1 की जगह आएगा 0 minus p, then you would have 0 यहाँ लेंगे तो it would be minus q, then ये लेंगे तो 1. Now that's obvious. और साथ में h है, so we have to multiply or divide this, or divide it, multiply it by 1 by square root of 1 plus p square q square. Then you just have to, now again you've got these three numbers, you've got RUU, RUV, RVV, you take their dot product with this n vector and you would get, it's not very easy, so you will get L, M and N. I mean to say like this. Okay, what I'm trying to say, you already have this RUU. What is RUU? 0, 0, R. 0, 0, R vector. You have to take the dot product with n. 0, 0, R को इसके साथ dot product लेंगे. So इसका मतलब तुम्हारा जो second fundamental magnitude होगा, वो होगा L होगा बराबर RUU dotted with n. It is nothing but, इसके साथ करेंगे तो it will be just R by H. और R by H, या simply H की जगह हम लिख सकते हैं root of 1 plus p square plus q square. Similarly, M would be S by H, and of course N would be T by H. So these are very easy to evaluate. If you have the equation of a surface, then it's very easy to evaluate. It is very easy to evaluate these first order and second order fundamental magnitudes. Now last time when I was taking your Viva, I realized that you don't know much about, so I realized that you had some problem with this triple scalar product. You don't know what is a triple scalar product, which is very strange because you do it in your 12th class. So I want to take this out. Should I? Okay. Now select कहाँ से करते हैं इसको? So if I take these two, I would need them. First and second order fundamental first. Okay. Okay, टाइम लगता है इसमें, क्या करें, इसको ज़रा यहाँ रखते हैं थोड़ी देर के लिए. Okay, we would need them. Okay, now what I was trying to say is that there is something called a triple scalar product of vectors. So if you have three vectors, let me write in 3 dimensions. Okay, if you have 3 vectors in 3-dimensional vectors, then you can think of their triple scalar product. Suppose A, इसको क्या हो गया? Okay, so suppose A is equal to A1, A2, A3, and B is another vector B1, B2, B3, and C is another vector 3 component C1, C2, C3. The triple scalar product usually denoted by the square bracket A, B, C का मतलब होता है, जो कि नोट्स में दिया हुआ था, पता नहीं तुमने कैसे मिस किया. It is A dot B cross C. So it would be a number, and it would be simply the matrix, determinant of the matrix A1, A2, A3, B1, B2, B3, and C1, C2, कौन है यहाँ पे, इससे determinant. तो ये होता है इसका वैल्यू. यहाँ पे यूजुअली हम कॉमा रखते हैं, यहाँ कॉमा होता है, ठीक है. Okay, this is what is triple scalar product. So you know that जैसे last time तुम कह रहे थे, equation of the tangent plane is basically osculating plane at a point small r is this, comma r dot comma r double dot. This triple scalar product is equal to 0 is equation of the osculating plane. By that we mean this. If you take, इसका मतलब है r minus r as a vector, we take its dot product with r dot cross r double dot. And if this is the equation for this is the generic point or the general point, generic or general point, any point, the arbitrary point on the oscillating plane, and small r is our chosen plane on that curve. Now I have come back to the curve. I just wanted to clear this thing. Now there is something that you can see now. That is, if you interchange any two rows or columns of a determinant, the sign gets, we change the sign. So this should be equal to, then now this should be minus, if I interchange b and a, this should be minus that. And if I interchange twice, right, if I interchange twice, it should come back to the same. It should be also equal to this triple scalar product, should also be equal to, if I write it as b c a. So ABC triple scalar product should be equal to BCA. Actually, if you change them cyclically, and you send A to B, B to C, and C to A, so it would remain the same. And if you change interchange two things, it should change it as sign, because it is basically the determinant of three vectors. So having done that, so we can just evaluate certain triple scalar products for our surface also. So I hope you need go through it again. Okay, for our surface, I have just like this. If I want to evaluate now the triple scalar product n r sub u comma r sub v, this triple scalar product, now this should be nothing but n dot, right, n, no, let me not write it as n, okay, okay, this is as per my definition जो मैंने ऊपर लिखा था, n dot ru cross rv, but ru cross rv is nothing but n dot n vector multiplied the scalar h, and where h is nothing but the mod of ru cross rv. But n is a unit vector, so n dot n is 1, so this is just equal to h, right? Similarly, I can talk about this. And the triple scalar product would be, say, ru comma rv comma r sub uu. If I take this triple scalar product, I can write it as, because dot products commutes, I can write it as easily as ru cross rv, okay, dotted with ruu, which would be, of course, this is hn ru cross rv, then I dotted with, r sub uu. So this is just n dot ru is second fundamental magnitude L, so it is HL, because n dot ru is L. Similarly, so what I have done so far is I have found this triple scalar product n r sub u comma r sub v is nothing but h, and I have another triple scalar product, that is r sub u, r sub v, r sub uu, this is u here, this is equal to h times L. L is our second fundamental magnitude. Similarly, I can easily evaluate ru comma rv, then I have ruv. This can also be evaluated, and it can be, we would use them later, that's what I am writing it. So this is hm, where m is the second order fundamental magnitude. And then the last one, I can also evaluate R sub u, R sub v, triple scalar product RVV. This can also be evaluated to be Hn. Now Lm and R are our second order fundamental magnitudes. Then I can also think of, although they are not required, let's leave it there. So these are certain triple scalar products that we can think of once we have these vectors. Now you have to remember now what the situation is. So I have got a regular surface or a point that is regular on a surface. I've got a tangent plane at that point, right? Which is spanned by RU and RV, means there are two non-collinear vectors at each point. One is RU and then I have RV, and then I have a unit vector which is perpendicular to this tangent plane. So it is a situation like we had in the curves, the Serre-Frenet frame. So I have got three vectors which are linearly independent in R3 space. So I can think of it in a surface here. It forms a local frame of reference. This RU, RV and N can sort of form a local frame of reference, and we can write sort of any vector in the vicinity in terms of RU, RV and N, because it is a basis for R3. So therefore any point, and hence the local points here can be written in terms of these three vectors. Okay, so we move to the next thing, and I hope you can now do these triple scalar products and these evaluating these first and second order fundamental magnitudes. It shouldn't be difficult. Okay, now we talk about surface. Now I've got an N. Now remember this actually determines how the surface is sort of behaving, this unit vector N, because it is of magnitude 1. So suppose it has a direction, it is magnitude same है, तो होगा क्या, इसका direction change होगी, है ना? So at this point अगर ये same रहता है, जैसे suppose I have a plane पे situation होगी हर point पे n would have, of course magnitude तो same है ही, लेकिन direction भी same होगी plane पे. So different जो बाकी surfaces है वहाँ पे जो n होगा ये हर एक पॉइंट पे इसकी डायरेक्शन चेंज होगी, मतलब if the surface is curved, if it is not flat, if it is not just a plane. So n actually encodes the information how the surface is going around, मतलब from when we move from one point to another point, what's happening, in terms of the curvature. So this unit normal actually, so I draw a tangent plane here and tangent plane here. Now how tangent planes are changing from point to point would be given by how the normal is changing its direction from point to point. Okay, so now let's go take it further. Now we know that if you have a vector of constant magnitude, which it is, now it's of magnitude 1. We have done it in curves. If you have a vector of constant magnitude, it's rather easy to prove. It is always perpendicular to its derivative. And if a vector is such, its magnitude is fixed, only its direction changes, then it must be perpendicular to its derivative. And in the case of n, because now it's a function of two variables, it must be perpendicular to its derivative, differential, because we are in two dimensions. So since n is of constant magnitude, I can say that n, if we take dot product with dn, right, it should be equal to 0. So let me call this equation 1. So we can derive it from something called Weingarten equations. So, but dn is equal to, because it depends upon u and v, and we are assuming the differentiability of almost everything. What is n? N is basically Ru cross Rv, of course, divided by this magnitude, which is a number. So it depends upon u and v, because R depends upon u and v. So it's a function of u and v. And if we assume that it's differentiable, which we do, so then dn can be written as, the differential is always written as n sub u du plus n sub v dv. It is just the definition of the differential, which depends differential of a function which depends upon two variables. It is the same thing we write now, del f in our first semester. It is equal to del f by del x into dx plus del f by del y into dy. It is the same thing. Okay. Okay. So let me write this because I might need this space. Oh no. Oh, in a garbad. Okay, this is my dn. So now look at this. ये जो dn है, so it is perpendicular to n. But n, everything that is perpendicular to n lies inside the tangent plane. Because all the vectors that are perpendicular to n, because n is perpendicular to this plane, means all the possible vectors that could be perpendicular to n must lie inside the tangent plane. Now dn is perpendicular to n, therefore this dn, whatever this is, it must lie inside the plane, the tangent plane, which is spanned by our tangent plane. Everything can be written as a linear combination of Ru and Rv. So dn now lies inside the plane which is spanned by Ru and Rv. Okay, now what I do, I have got this equation, n dn is sorry so is equal to 0. So n dn is equal to 0 और dn is equal to जो हमने अभी किया था, so it should be n sub u, मैंने क्या लिख दिया, okay. Now what I am trying to say, n जो है dn lies, ये जो dn है ये कहीं पे मेरे टेंजेंट प्लेन में लाई करता है. It means dn must be some combination of alpha Ru plus some beta Rv. And remember that dn lies there. Therefore, no, I can also think other than that. No, I can also separately think without any reference to this thing that n dot Ru is equal to 0 because n is perpendicular to both Ru and Rv. So if you differentiate it partially with respect to u, then you should get, using the product property, the dot product differentiation जो होता है, it's just like ordinary product. You differentiate this partially and keep it as it is, and then take the sum, then keep n as it is, and differentiate r with respect to Ru with respect to u again. So this should be 0. It means that n sub u dot r sub u is equal to minus n dot Ruu. So which is nothing but L. So it is minus L because this is our second order fundamental magnitude Lmn. उसमें L होता है. Similarly, you would have, if you differentiate it with if you differentiate this partially with respect to v, you would get n sub v dot r sub u is equal to minus m, and similarly if you partially differentiate n dot r sub v equal to 0, you differentiate it partially with respect to v, you will get n v dot rv is equal to minus small n, capital N. Okay, this is our second order fundamental magnitude. And of course you could also get, if you partially differentiate with respect to u, nu dot RV. Just a minute, you've got NV dot NU dot RV would be equal to minus N. So these four equations we will get by partially differentiating these two equations, n dot Ru equal to 0 and n dot Rv with respect to 0 with respect to u and v. You are differentiating them partially with respect to u and v. So we get another expression for the second order fundamental magnitudes. You can write n now as minus nv dot Rv, or you can write m as minus nu dot Rv or nv dot Ru, or you can write this L as nu dot Ru minus, of course. So hence equation 1, hence we can write now. So we can write our equation 1. What was our equation 1? We was n. We can write this equation, n dot dn is equal to 0. We can write it as n dot nu is equal to 0 and n dot nv is equal to 0, because it is because nu and our dn lies in this plane Ru Rv. So as I said, so if you because n is perpendicular to dn, it means it must be perpendicular to, we have got something called, what was dn equal to? Dn was basically n sub u du plus n sub v dv. So it's a linear combination of nu and nv, and it's partial with respect to u and partial v. So I must have, this should imply that n sub nu is equal to 0 and n sub nv is equal to 0, because u and v are independent parameters. That's from the very beginning, from the definition of the surface we have. Now we have got this thing. Now it means that now nu जो है, it is perpendicular to n, so it lies inside the tangent plane, and any vector inside tangent plane can be written as a linear combination of Ru and Rv. Similarly, n sub v also lies in the tangent plane, therefore it also can be written as a linear combination of Ru and Rv, because Ru and Rv are the spanning vectors of the tangent plane. Okay, so what we do now, suppose I write now nu as a linear combination. You take a some scalar times Ru plus b some scalar, b times Rv. A and b are just numbers, scalars, some scalars. Now what I do, if I take its dot product with Ru, if I take the dot products of this equation with respect to Ru, both sides, so what you get? You will get on the left hand side nu dot Ru, right? Then I would have a into Ru dot Ru, that is just E, right? Plus b times, then you have Rv dot Ru, that is just F. So this is the equation I would get. And remember, nu dot Ru, just now, if we go to the previous page, what was the previous page? Yeah, nu dot Ru is nothing but minus L, right? It is equal to minus L, so I can write here minus L. So I got, what do I get? From this I get the equation AE plus BF plus L equal to 0. So this is one equation that I get. And remember that what I am trying to say, we want to get the values of A and B in terms of known quantities. A and B are unknown scalars, no? So I wrote nu as A times Ru plus B times Rv. So I want to find these numbers in terms of fundamental, first order fundamental or second order fundamental magnitudes, which I already know by evaluating the matter point on the surface. So once I have done that, so this is one equation. Now another equation would be, I could have instead of taking, instead I could write, oh sorry, I could write I could write NV as some linear combination of mm, RU and RV. Had I done that, or I could just take now. No, I just first, that's one way. Another way of doing it would be I take the same equation, and now if I take this equation, what was the equation? Let me write it here. Nu is equal to some a times r sub u plus a b times r sub v. I want to evaluate what these numbers should be in terms of the numbers that I already know. Now I have dotted it with RU, I get this equation. Suppose I dotted it with R sub V. The equation I would get, I take the dot product with respect with RV of the same equation. So I would get AF plus BG plus M is equal to 0. Now this is where I wanted to get, because now I can find these ABs in terms of E, F, G and LM, because basically we just solve, these are just equations in two variables, x and y की जगह है and b. So if I apply the cross multiplication method that you know from your school, this would be just a would be fm minus gl divided by eg minus f square, and if you know that is just h square, and b would be equal to, just doing the cross multiplication, fl minus em divided by eg minus f square, and you know that this is actually equal to h square. Okay, so once I got this, it means I can write now nu in terms of ru and rv, and if I do that, oh shit, if I go here, so I have got now this n, therefore can be written as, let me take the next page. So therefore I can write nu as, I can write now n sub u as, now a की जगह मैं लिखूंगा, what was that? I have got fm minus gl divided by h square into r sub u plus fl minus em divided by h square times r sub v. So this is writing nu as a linear combination of ru and rv, or I could multiply both sides by this scalar h square, which I know, and then I can write this fm minus gl times r sub u plus fl minus em times r sub u. How did I get it? I just first wrote n sub u as ARU plus BRV, and then took its dot product, respectively first with RU and then with R sub v, and from this I got this equation. Similarly, I can take NV and write it some linear combination of RU and RV, because I know it lies inside the tangent plane. And then I again do the same thing. I take its dot product with RU, let me write it as D, and then with RV, then I solve those two equations, and from which I will get an equation of this type: h square n sub v is equal to fn minus gm RU plus fm minus en, which are fm, ef, gl, lmn. They are our first and second order fundamental magnitudes. This would be en r sub v. So in this way I have been able to write the partials of my unit normal in terms of the partials of r and ru and rv, the ru and partials of r. So these are called Weingarten equations. We call them Weingarten equations. They're important because, as I said, what is happening at a point on a surface in terms of its curvature is encoded in how this n goes around. This is a vector of magnitude 1, how it changes its direction as I move from one point of the surface to another. How this n changes tells us what is happening on the surface. So it's important that we want to write it in terms of something that we already know as a linear combination of Ru and Rv. So these are Weingarten equations, but we can just reverse the process. And we can now solve. We can solve. We can just do. As you know how to solve two equations, what you would just multiply by something so that one term cancels out, and you can solve. I mean to say, you can solve these two equations for Ru and Rv. And if you do that, you will get t square R sub u. You can also solve them for Ru and Rv. You will get Fm minus En times n sub u plus Em minus Fl into n sub v, and similarly t square into r sub v can be written as Gm minus Fn times n sub u plus Fm minus Gl times n sub v. So these are important because we can go from one set of vectors to another set of vectors, one basis to one local basis to another local basis. So t square, t square is nothing but t square is a shorthand for ln minus m square, where ln and m are second order fundamental magnitudes or numbers. We have already talked about them. So this is what we get. So there is another thing we can do actually. If you take the cross product of nu and nv, if you take the cross product of equations, these two equations that I put inside the box, you would get this thing. Let me take another page. So from these two equations, from the Weingarten equations, you can actually take their cross product and get h raised to power 4 and u cross nv is equal to, it would be a lot of things, so but you do them from notes. It would be Fm minus Gl multiplied by Fm minus En. You do them from notes, so into Ru cross Rv, then I have plus Fl minus Em into Fn minus Gm into Rv cross Rv. And others would just be 0 because, okay, then when you simplify it, it would be nothing but, let me write it here, h cube into t square into n, because Ru cross Rv is n. The Rv cross Rv is minus, so you just take the n out and evaluate these numbers. So you will get h cube into t square, which would give us nu cross nv is equal to what? Nu cross nv is equal to t square divided by h times n. Again, what does that mean? N is perpendicular to both nu and nv. Look, that's what we started with and got here. So let me stop it here. Till the next time, God bless you.